understand ordinary least squares regression, we start with its primary objective, taking a variable we want to explain and mapping it to a specific set of explanatory variables. Look at this two-dimensional scatter plot. The mechanical goal of regression is to position a line through these points so that the vertical distances between the actual data and the predicted line are as small as possible. We call each of these vertical gaps an error term, or residual. To find the optimal fit, the model squares each error term to remove negative values and penalize larger gaps, then solves for the line that minimizes that overall sum. For this mathematical engine to produce perfectly valid estimates, we have to strictly enforce three fundamental statistical rules. First, every single error term must be completely independent of the others. Second, we require homoscedasticity. The variance of the error terms must remain perfectly constant across all observations, regardless of where we look on the line. Third, the error terms must always follow a normal distribution. Fitting a single line on a flat plane is straightforward arithmetic, but predictive models rarely rely on a single input. We need a way to take this simple geometry and scale it to process an infinite number of explanatory variables across multiple dimensions. This split screen shows our two approaches. On the left, the simple scalar formula divides the covariance of x and y by the variance of x. On the right, the multiple regression formula uses matrix algebra to calculate the inverse of x transpose x multiplied by x transpose y. While they look vastly different, they execute the exact same logic. The matrix equation is simply the covariance to variance ratio mapped to handle multiple dimensions simultaneously. We begin with the baseline scenario, simple linear regression. This applies when exactly one explanatory variable, where k equals 1, is used to predict the response. In this single variable environment, the estimated slope of the line is directly proportional to the correlation between the two variables. This excerpt defines the slope estimator, beta 1 hat, as the quotient of the sample covariance of x and y divided by the sample variance of x. Because both involve dividing by n-1, those denominators cancel out, making the distinction between biased and unbiased variance irrelevant. Looking at the summary statistics in example 2b, we see how this mechanically processes data. We drop the raw sum of x squared, 408, directly into the expanded variance denominator. Then we slot the sum of x times y, 462, into the expanded covariance numerator. Here in the solution, the formula grinds through those substituted sums, subtracts the offsets for the means, and outputs a final slope parameter of 0.65. In a one-dimensional environment, finding the line of best fit is a mechanical reduction of raw data sums into a precise, predictive ratio. When we add a second, third, or hundredth explanatory variable, k becomes greater than 1. The scalar arithmetic breaks down, forcing a dimensional shift in the mathematics. We organize explanatory variables into a design matrix, X, with n rows and k plus 1 columns. We insert a leading column vector consisting entirely of ones, labeled x0. This mathematical placeholder accounts for the beta 0 intercept parameter, pulling it outside the sum. With our data structured as matrices, we translate the algebraic operations. We can no longer simply divide by the variance. Instead, we multiply by the inverse of the matrix formed by x transpose times x.
This brings us to equation 2.4, the generalized least squares estimate for beta. Looking closely at the components, the inverted x transpose x matrix isolates the internal variance among the explanatory variables. The second component, x transpose y, captures the covariance between those explanatory variables and the response. The operations mimic our simple scalar ratio. We are still evaluating covariance against variance, but mathematically scaled to process infinite dimensions. This matrix system has a strict mathematical vulnerability. For the formula to execute, the x transpose x matrix must be invertible. If there is a linear relationship among the column vectors, it creates collinearity. This renders the matrix singular, and the regression fails. The text here details exactly how this happens, pointing specifically to the danger of using categorical indicator variables, commonly known as dummy variables. If we assign an indicator variable of 1 for male and 1 for female, adding those columns produces solid ones. That perfectly recreates the X0 intercept column built earlier. This overlap is perfect collinearity. The matrix becomes singular and non-invertible. To sidestep this trap, we enforce a rigid rule. When dealing with m possible categorical values, you must include exactly m-1 indicator variables in the model. A predictive model relies entirely on mathematical independence. Feeding it redundant data destroys the matrix's ability to isolate individual variables and calculate a solution. Returning to our foundational rules, remember the requirement for homoscedasticity, constant variance across all error terms. Real-world data frequently violates this. We often encounter heteroscedasticity, where the variance of observations shifts unpredictably, rendering standard estimates unreliable. To force compliance, we deploy a mathematical adaptation known as the weighted least squares estimator, shown here as equation 2.5. This formula introduces a new component into the architecture, the diagonal matrix W. W maps the precision of each individual observation based on its known variance. Points with low variance receive high weights, while highly volatile points receive low weights. Mechanically, sandwiching the formula with W aggressively penalizes the high variance data points and prioritizes the most precise observations. Ordinary least squares matrices do not simply break when faced with bad data. They can be engineered to actively isolate and suppress volatility. Rather than altering the internal matrix architecture, an alternative approach is to transform the response variable, y, directly. This excerpt introduces the Box-Cox family of power transformations, detailed in equation 2.6. By applying a natural log to the y variable, we manually levelize the variance and pull severely skewed data back into a normal distribution, forcing compliance with our initial assumptions. Table 2.1 maps this complete arsenal of linear model operations. It begins with the foundational scalar formulas, establishing the baseline mechanism for processing one-dimensional variables. It steps up to the matrix generalization, deploying matrix inversion to handle complex multivariable environments. And it concludes with the structural adaptations, weighted least squares and Box-Cox transformations, which correct the model when foundational rules are broken. Linear regression operates as a unified dynamic mathematical machine, capable of scaling from basic arithmetic to advanced self-correcting matrix operations.
I noticed that you seem to understand the concept, yet you still haven't liked or subscribed. Interesting. I wonder why.